All right, so we want to talk about the fundamental theorem of calculus. This is a bit of a revision. We're going to, what is it called? A reprise. That's it, it's a reprisal. We're going to come back to the fundamental theorem of calculus because we've noticed that in the Calculus 30, there's a specific type example that we didn't really get to. We were pretty broad when we talked in Calculus 30. Now we want to get into just a little deeper because we came across in the AP exam, practice exams, we came across a question that looked an awful lot like one of these examples. And so we want to go over specifically this example too. We want to take a look at this so that we're prepared and so that we've seen this notation before. But, whoa, too far. Anyways, so the connection, Newton and Leibniz, there's an astonishing connection between integration and differentiation. This connection started the mathematical development that fueled the scientific revolution for the next 200 years. Still regarded as the most important computational discovery in the history of math, the fundamental theorem of calculus. So from what we know of the fundamental theorem of calculus, we know a couple things. The first part here says this, is that if we have a function and we integrate the function, we have something called the antiderivative. Or if you take the derivative of this function, you should get this function, right? So here's the point is that we have a function, and if you integrate, that means you kind of go back up the ladder, you get something called the antiderivative, or we call it the integral, right? So if you have an integral function and you take the derivative of that, you can get the original function back. And of course, if you take the derivative of the original function, you have the derivative. So we have the integral up here, differentiate to get the function. Differentiate again to get the derivative. If we start at the bottom of the derivative, right, if we integrate, we can get the original function back. And if we integrate again, then we get the integral at the top. Right? So we see that. Now, the reason why I want to come back to this, and this looks pretty straightforward, but let me just zoom in a little bit on this. What we have to notice is this part, the limits of integration. So I'm not there, yeah, it's going to show up a little bit. The limits of integration. So this is A, this is some A value, and it's actually the number that would be the beginning of the interval. Okay? And so this number value here, it almost really doesn't matter what that number value is when we're actually looking at examples. What's important is that this upper limit is x. Okay? So if we have, let's think about it. Let's think about it this way. I'm going to go back to my notes here. Let's get a fresh page. So if we have some a value here and we have some function like this, right? It doesn't matter where we go to. It could be here or here or here. Let's not think about b for now. Let's just think about some x value, right? So there's a relationship between the integral, which we said at one point was the area under the curve, right? This is the integral of the function f of x with respect to x, and this is f of x, all right? So the area underneath. Now, if we started at A, and let's say this was B, then the specific area would be from A to B, right? Let's say we wanted to know what the area was all the way over to this point, and this was C. Well, then we'd have to change this upper limit of integration to find that exact area from A to C. We'd have to change this to C. Are you with me? Mm-hmm. So if we don't know where we want to end, and we're just stating general terms, then if we go to just some random value x, then you can kind of see how we need to keep a, but then this upper limit just stays as x. And we can go kind of as far as we want, and the general statement would be this. The antiderivative of f of x equals this. Okay? All right? So is that making sense? The upper limit is not an actual value. In general terms, we just stated in general terms, this relationship in general is just like this. We have some number value where we're going to start, and then it can go to wherever. It can go to here, or here, or here, or here, or here, just some value x. Whatever that x is, we can actually put a number in there and find an exact value, but for now, that's the general relationship. Make sense? Okay, so how does that, my question I guess is, and what we have to look at, is how does this play out, in, in examples, okay? So here we go. We're going to get, sort of past all this stuff. Okay, well this is interesting here, right? The derivative of the integral. So remember, the integral, we said the integral and the derivative are almost like opposite operations, right? If we start with a function, f of t in this case, and we take the integral, right? That's how we find the integral. But if we take the derivative of the integral, we get the function back, right? So it's kind of like we're taking the derivative of the integral here of f of t. Now, because we're going from a to x, this becomes f of x. So this is kind of a second way of looking at it that we didn't really do in just Calc 30. We didn't really kind of go this deep into it. I don't want to mess you up with the notation, but we did say that, taking the integral and then taking the derivative of that, we can get back the original function. So this is what this says. But notice how when the upper limit is x, then this f of t changes to f of x. Okay? So the derivative with respect to x of an integral taken from some value to x is actually just f of x. And so that leads us kind of to the example that we saw in the university calculus class that we visited. All right. Now, I kind of don't want to focus on this one example yet, but it was this example that was very similar to the one that we saw before, and very similar to one that was in the practice AP exam, right? So let's just. Oh, is this the one? Shoot. Example 2. That's the one that's a little bit more complicated. Okay, that's got the x squared. All right, fine. Was there a different one that's... Okay, we are actually going to look at example 1 first. Okay, so let's just look at this one first. The reason why we're going to start here is because this fits the bill here with just an x right there. Remember, pi, that's not a variable, that's a number. Okay, that's a constant. And so if we have negative pi here, it doesn't matter what this is really. If it's pi or if it's 0, this actually does not matter. What matters is this, d dx, an integral with an upper limit of x. If this is the case, then this piece right here, the integral part, right, basically cancels off this part. I'm sorry, the derivative part cancels off the integral part, right? And what we're left with is just cos of x. So d dx of an integral with an upper bound of x, we get this function back out, cos of x. This one here, d dx, doesn't matter what this number is, forget about this number, forget about it. If this is x, then the answer is 1 over 1 plus x squared. So you're taking the derivative of the integral, you just get this function back, that's it. When this is just x on top, that's all it is.
Shouldn't you have to do something with the limits?
No.
Why does the bottom number or the top or bottom number not matter?
Okay, why does the bottom number not matter? Well, the bottom number doesn't matter. Why does it not matter? Because it's just any constant on the interval. We're not actually, remember, the answer is cos of x. We're not actually finding a definite.
Yeah,
so the boundaries don't really matter so much. It's just sort of the representation. Yeah. So if we were finding definite integral, then certainly this negative pi would have to be our lower limit, and we would factor that in. And then this x, whatever your upper limit would be, so you'd have two actual number limits, then that would really matter. Then we'd have a number answer. Okay? All right, so example 2, this is the tricky part here when you have x squared as an upper limit. This is not x, right? And it's very important that we don't treat it the same. The answer is just not cos x squared. Okay? It's not that simple. The reason why that's not that simple is because this x squared, right, we actually have a derivative, don't we? If this was u, and we thought about this as d over du, right, because we would have to do that, d over du, if this was u, then we have to consider that whatever x or whatever u is, there's a derivative involved. And so when we take the derivative, we have to consider the chain rule and how that would affect things. So if this is just old x, So if it was this one, this is what we just did, from whatever, doesn't matter, to x, right? And this was t dt, whatever. Then the answer would be, if we took the derivative there, it's just cos of x, right? But this is not x, this is x squared. So that adds a new level of just a complexity. So we're going to change this x squared, we're going to make it into u, okay? U substitution. It's sort of like the u substitution, right? It's a little bit different. But when we're substituting with the limits there, it's sort of similar. Okay. So we must therefore apply the chain rule when finding dy dx. So if we want to do this, d of y with respect to x, see, here's the thing. This is not x anymore. That's not x. That's u. So first of all, we have to find dy with respect to u, and then chain rule says multiply that by du with respect to x. So look at how that changes things here. Okay? So if I change, and I'm going to change colors here, if I change this x squared to u, now I have to change this x to u. Everyone see that? And this doesn't matter, you can just leave this all alone. But this is the kicker right here. Now I'm not dx anymore. And I really want to find dy dx, or d dx, right? And so d du is not going to cut it. So what I have to do is, and again, we haven't studied this too much. I didn't really focus too much in the Calc 30 with you when we got to this initially about the Leibniz notation. But this is where it shows the chain rule actually makes a lot of sense, because I want dy over dx. So if I have a u in there, all right, see, look at this du, you see that? Kind of cancels each other out in a sense, and you end up with dy over dx. So I can substitute, take that x out, I can put a u in there. But then I have to figure out, I have to multiply by the derivative of whatever that u is. So let me get rid of this scratch here. So if we do this, have a u there, I have to multiply by du over dx, because that will then give me d over dx. See, the du's will really cancel out. And if I've taken care of this and made this an x, then I'm going to be able to easily see what I've got here. So du, or d du, when we have a u here, is just cos of u. You see that? So now we can just go ahead and substitute this t in for the u, so it's cos of u. But we can't forget about this right here. So that's when, now this is really important actually, so from this part right here, do you get this? Because that's the big part. That's the big kind of like step. If you get that step, then you're good. So with all of this inside the brackets, this just becomes cos u. See that? Because I have this and I have this, so the u now goes there. That's why I get there. The du dx is easy. U, as up here, was x squared, so du is 2x. So that's where this comes from. That's du with respect to x. You see that? And of course, if I'm now back in terms of x, then this u now has to be written in terms of x, and that's where I get my x squared from. And that's how you get 2x cos x squared for an answer. Yes? Do you have a question?
Yes. So, if du is 2x.
Okay, so let's try exercise 9. Here it suggests that we try exercise 9. Here is question number 9. It's just like this example. Okay? So, I would be tempted to find the derivative. Sorry, we're actually finding, it says find dy dx, of course. This is what all the questions are, okay? Find dy dx. So, it would be very tempting when we take the derivative of both sides with respect to x, right? It would be very tempting to just say, hey, my answer is ex squared. But you can't do that, can you? Because this is not just a plain old x. So we can't do that. This is bad. But what we can do, girls, listening, what we can do is change this to u and change this to u. All right, so we have, again, this lower limit doesn't matter. That's u. if I do that, what do I have to also do? If I change this to u, I'm almost there, but I have to what? Times
du over dx.
du with respect to x. Exactly. Now, why do I do that? Because I want this du and this du to be gone, and I want to then just kind of focus on this with respect to x. You see? Okay, so we're getting close here. We're getting close. So now I can go ahead and I can just sort of, this is a u and this is a u. So according to our, look at the example we just did, right? Once we have this, we can now go ahead and just pretend that, just put the u in there basically. So this is going to be e to the u squared times, now what's the derivative of u? So u is what? U is x squared. Du is 2x.
Wait, did you just change t to x?
I just changed t to u because I have a u here and a u here. See, you are here and you are here. You are in two places at once. Oh, congratulations.
Wait, is there any chain rule that happens on the t's?
Okay, good question. Is there any chain rule that happens on the t squared? The t squared, don't think about this as a separate variable, really. Remember, we're just looking for, with respect to x, it's a good question, but let's just think about this as time. Okay, so think about this as time on the x-axis there. I think if that's appropriate. And we want to make sure that we differentiate with respect to x. So no, this letter here doesn't matter. It could be anything. We're just focused on what do we want to differentiate with respect to, and what is our substitutional variable. So yeah. No, now what we do, you got to make, no, don't worry about the t's at all, really. I mean, the t's are immaterial, really. So, but now what we do is we want to make everything in terms of x, so the u does have to be substituted in for the x. So that's actually x squared times 2x, right? Which is e to the x to the fourth, and then times 2x. So you might want to write this as d over d x, or dy over dx is 2x e x to the power 4. And I believe that should be the right answer. Does everyone agree with that? Anyone, did I make any mistakes there while I'm talking and congratulating you for being in two places at once? Did I miss anything while I was doing that?
How can we ignore t?
How can we ignore t? Okay, it's a good question. But listen. Okay, so remember going back to the fundamental theorem here. Remember the fundamental theorem, which I do not have on here, but I have in my book. Okay, where did that go? So look at this. The fundamental theorem. See this? It says that if we have d dx of the integral from a to x of any function, doesn't matter what the function is, it can just, like these variables, honestly, they don't have any bearing. Because we have an x here and an x here, we can actually, this kind of undoes this, right? And so because we're dealing with this with reference to x, then the x just gets transferred into there. Okay? So this could be f of w dw or f of k dk. Doesn't matter. You're just looking at this here. This is sort of a, I don't know if you want to call it like just a substitutionary function, just like, hey, this is just any kind of given function. But if we're going to differentiate and integrate with respect to x, now this function is a function of x. This is now the preferred variable that we're looking at. So these letters don't really matter. And to be honest with you, that's the best explanation that I got right now. There's better explanations out there, and if you ask me 2 years from now, I might be able to give you a better answer, but that's all I got right now. All right?
Do you use that as an assignment?
As an assignment?
Yeah.
As an assignment, what, for me or for you?
For us.
How about for you? Yeah, you come back in 2 years and give me a better explanation about why the t's there.
Make a video
Okay.